Cattles? 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 Cuddles? Cuddles? Cuddles?
Hello. Hello, 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 hello. Hi, everybody. I am so sorry that took so long. Hi, it's so good to see you. How are we doing? Hello. Hello. Okay. Yeah, I'm very sorry. We had severe storms. Like, we still have some flooding going on. Most of the trains were shut down. It was kind of wild today. It was kind of crazy. So, needless to say, the final touches that I was putting on our presentation for tonight, Dissim appeared. They RUNNOFT'd. Hang on, I need to see. That needs to go away. Something is not muted somewhere. Okay, YouTube, you guys are live. Kick, are you guys live? You guys are, in fact, live. Yes. Okay, cool. You guys are live. And Twitch is live. I need to make sure that that's muted. I got it. Wish we got any... Oh my god, see, hello! See, it's been ages. How are you doing? Are you still getting that echo? Class is in session. I was going to make a joke about being what, but got distracted by the echo. Valid. Very, very valid. Very, very valid. Hey, Firefly, thank you for checking in over there. Okay. I appreciate you so much. Shit, but thanks for asking. If I can do anything, I know I can't imagine that I can do anything, but if I can, please, please, please let me know, okay? Okay. So, how's the audio level for you guys? Are you guys okay? I hope you guys are okay.
Cuddles?
Miss Vaughn! Y'all in the back, settle down now. I know. Here for the science stuff? Good. Okay, cool. Well, we will try to make it fun and entertaining. And Miss Vaughn, I really do appreciate you being here. Thank you for being here. Okay, chat, so here's the deal. I'm going to experiment with a couple of things tonight. The first thing that we are going to experiment with is I am actually going to give you thank you for the hydrate. A college, like, this is a lecture that I give to colleges around the US. Yes. So, we're gonna experiment with this. If you guys like this style with like an actual presentation and not just me randomly pulling up images and showing you stuff like that, then, and you want, how are we going to do this? I will essentially give you the entirety of a introduction to geology and geoscience. There's a non-zero chance DG has been at my campus to look at the rocks. There is, in fact, a non-zero chance that I have been to your campus, Jesu. Actually, very, very likely. So if you guys like this is the requirement. This is the quote homework. I need to know if you guys like this style, if you like the more chaotic, like all over the place, Google searching style. And if you would like to get the equivalent of a college geology 101, maybe I'll do like structure I can basically give you an undergraduate geology education for free on Twitch, and we can just do like one topic a week and cover all of the topics that you would cover in a college setting, in a university setting. So with all of that in mind, please keep in mind that what we are about to cover, is more of a, can it count for your minor? I am not associated with any specific university, so no, it can't count towards your minor, but it can give you a really, really, really nice basis for when you do take these classes for your minor. Okay, cool. So, welcome back. We're here. It's Science Sunday. And today, we're going to be covering something that is a little more like a senior year seminar, like a pre-graduate level seminar in an Earth system known as the carbon cycle. And it's one that connects everything. You know about the water cycle, I'm sure. You know about, the rock cycle, because we've talked about that before. But this one connects rocks, trees, the ocean, the air you're breathing, the gas in your car, and even a bag of potato chips. Because all of it is running laps around the planet on the same element. So we're going to be talking about the carbon cycle. And we're going to take a while to talk about it because the version that most people get in school stops right where it gets good. So honestly, what you usually get to see is an arrow diagram. CO2 goes into a plant goes into the animal gets eaten by a human or dies, gets buried, yay, cool, whatever. But what it leaves out is that this is the same cycle that scientists can use to look at the air and tell you that the carbon in it came from a coal plant, and not a volcano. Coal plant being like a power plant and not a volcano. And so that's some of the science that we're going to cover tonight. But here's the hook. And this is what I kind of love about the carbon cycle and what I hope you guys will love too. Carbon is the reason that you're alive. It's it's also this reason that climate is changing. It's the same element. It's the same cycle. We didn't invent a new problem out of nowhere. What we did was we took a system that was running on a time scale of millions of years, and we started running it in a couple of hundred. And that's the whole story in a single sentence, in a tweetable sentence that is, quote unquote, what has caused climate change. But by the end of this, you're going to be able to look at a power plant, a forest, a coral reef, and a bubble of air trapped in Antarctic ice, and you're going to be able to read all four of them as the same system. So, chat, drop an emote right now if you're locked in and you're ready for this. And if you're just tuning in, this is a lecture stream, so I really hope that you'll pull up a chair because we're going to nerd out together. Okay. Before we watch carbon move, we are going to have to, hang on just a second. Zoink, zoink, zoink. I need this down here like this. Perfect. Okay. So before we watch carbon move, we have to talk about why it's carbon that's pulling this job and not some other element, because it's not an accident. And it tells you something deep about why life looks the way that it does. Okay, so part one tonight, we're going to be doing this in 4 places at 2 speeds. So part 1 is, where is the carbon? Part 2 is how fast it moves, the fast versus the slow clocks. 3 is how it got knocked loose. And 4, what that does and what pulls it back. And we're going to talk about all of those. So here's the cool thing about carbon. It's the 4th most abundant element in the universe. After hydrogen, helium, oxygen, we now have carbon. On Earth specifically, it's more like the 15th most abundant element in the crust. So it's not that the planet is drowning in it. Shanir, thank you so much for filling up your card. Thank you, thank you, thank you. It's what the carbon does with itself that actually matters. So here's a property that's going to run through this whole whole shebang, right? A carbon atom has 4 spots open for bonding. 4. Now that's the magic number because 4 lets carbon link up in every direction at once. And that means it can build long chains in the form of hydrocarbons. It can build rings. It can build branches. It can build structures thousands of atoms long. And here's the key part. Those structures are always stable at Earth temperatures, for the most part. There are 3 exceptions that I can think of off the top of my head. But what they do is they hold together in a range where liquid water exists, which is the same range where life exists. So there you go. There's the periodic table of elements. And let me get my mouse. It's the 6th element, carbon, right here, right? 4th most abundant. And basic carbon, you get 6 protons, 6 neutrons, 4 open spots. What are the exceptions? I'll explain later. There are a few other elements that can also build chains like this. Silicon is the one that most people know about and they bring up most frequently. You can see right here. It is right there we go. It is right above or right before I'm sorry. It is right below, right here, sorry, right below carbon on the periodic table. And it has that same four-way bond trick, but silicon chains are shorter and they fall apart way easier, especially around both water and oxygen. So every time science fiction gives you silicon-based life, it's a great idea. It's a really fun idea. But carbon is genuinely built differently for this. Carbon builds durable, complicated stuff, and that's why it's the backbone of every single living thing that we have ever found. You, specifically, my dear viewers, are the 2nd most carbon thing in your own body after oxygen. Structurally, you are a very, very elaborate carbon arrangement that thinks about video games. So, I want each of you, aside from yourselves, to name something that you think is mostly carbon. Mostly carbon. Throw them in the chat. I want to hear what you guys are thinking. What is something that is mostly carbon? Wood, yeah. That has a carbon skeleton. Coal, yep. Yep. Anything else? Anything else that you guys can think of? Diamond, yep. Pure carbon. Correct. Metal. Some metals have carbon. Graphite is another one. Pure carbon. Same atoms. So here's the cool thing. Carbon, because it is so complex, or so complex a bond. Air that we breathe, yes, air that we breathe has carbon associated with it. So carbon atoms in the form of a diamond arrange in really, really rigid lattices. Graphite, like you would see in a pencil, is also the same exact atoms, but they have a totally different arrangement. So it's the same element. One's the hardest natural material in the world, and one rubs off on your hands. And that is carbon's whole personality. Wood, food, plastic, gasoline, you. A lot of the components, like carbon fiber, a lot of the components in F1 cars, carbon, all carbon skeletons. So what I want you to do now is I want you to hold 2 things in your head. Okay, we're going to move forward. We're going to, okay, so here you go. Here's your summary. 4th most abundant element in the universe, 2nd most abundant element in your body, and 1 backbone of every living thing that we know about, right? So the thing that I want you to keep in head, we're going to talk about diamond and we're going to talk about graphite and how they're the same atoms arranged differently. And fossil fuels are just old life, but both of those are going to make a comeback. Now, why is that? So we're going to talk about the two clocks. We have a fast carbon clock, which is on the order of years to decades, a human lifespan. That's all life, that's all air, photosynthesis, breathing, anything that rots and dies. Then there's the slow carbon clock. That's rock, that's deep ocean. It's anywhere from thousands to millions of years. That can include rock burial, volcanism, weathering of rock, all kinds of stuff, okay? And all of these things are arranged into one cycle known as the carbon cycle. At its absolute simplest, what a carbon cycle is carbon moving between four places. That's this diagram on the right, okay? We have the air, we have living things, then we have the ocean, and we have rocks. Carbon moves, it parks somewhere for a while, and then it moves again. The entire field is just where is carbon and how fast is it moving? And those four places have proper names and they're worth knowing because earth science uses them constantly. The atmosphere is the air sink. The biosphere is everything living. The hydrosphere is water, mostly the ocean. And then you have the geosphere, sometimes called the lithosphere, which is rock. Geosphere and lithosphere are not one-to-one. Lithosphere also talks about, hang on. I'm not going to get into that right now. The carbon is a courier that runs packages between all four of these. And the carbon cycle is the delivery route for that mailman, okay, that male human. And the single most important thing that I can give you during this entire lecture is that it's going at two different speeds. Like I said, there's a fast cycle and a slow cycle, and almost everything that matters about climate occurs at the boundary between those two clocks. So the fast cycle is life. And on this map, what I'm going to show you, so blue or yellow on this thing, this is from Berkeley. The yellow outlines the carbon cycle, photosynthesis, respiration, weathering, broadly speaking. Blue shows the interactions of carbon with one of the spheres and a process that can either produce carbon or bury carbon. Red are all of the boxes that are red are either anthropogenic sources, meaning human-based sources, or are, like in the case of volcanism, they are fast clock actions, right? So we have blue clock actions, which are slow actions, and we have the red, which are the fast clock actions. Now, I'm going to cover most of these things today, but it's important to talk about just a few. So the fast cycle is the cycle that we think about when we're talking about carbon as a life form. It's carbon moving through plants, animals, soil, and the air, turning over in seasons to decades, okay? A leaf grows, a leaf falls, a leaf rots, that carbon's back in the sky by the next year, by the end of that season, okay? But the slow cycle, the cycle that I work on, is geology. It's carbon locked into rocks and buried in the deep ocean, turning over across thousands to millions of years. And the way that that works is carbon goes into a rock and it can sit there longer than there can have been mammals walking the surface of the earth. So what I want you to think about is the boundary between those two clocks. And like paste it inside your skull. Fast is life, slow is rock. And when we get to the part where humans mess this up, the entire mess is that we built a machine for moving carbon from the slow side of the clock over to the fast side of the clock at a speed nothing in nature can match, okay? So let's actually talk through each of these cycles. So let's do the fast one because it's running, because you're kind of running it right this second. Hang on. Let's look at photosynthesis. So photosynthesis, very, very simply, if you have 6 carbon dioxide and 6 hydrogen or H2O water molecules, you add light, you get sugar plus C6H12O6 plus 6 free O2 atoms. Photosynthesis is often very simplistically described as plants absorb CO2. But we say that so quickly that we actually skip what's happening. A plant will pull carbon dioxide molecules out of the air, water out of the ground, and sunlight, and it builds itself. It literally constructs itself, cell by cell, out of those materials. It pulls gas out of the sky and it turns it into a wood. Now, here's a question for you. For those of you that are here right now, where does the mass of a tree come from? Like when a tree gains, quote, 500 pounds, where did the 500 pounds come from? Did it come from soil, water, or air? I'll wait. If a plant builds itself out of air, where does the mass of a tree come from? Any takers? Water? Water's a good guess. That's for sure. Anybody on the Twitch side? Soil and water? Okay. Anybody on the Kick side want to take a guess? If not a combination, then probably air because of the carbon. Yes. So the answer is in fact air. Overwhelmingly. A tree is mostly carbon that it pulled out of the sky plus a little water. The soil barely loses any weight as a tree goes. People have literally weighed the dirt to check. I've been involved in some of those studies. But Hazy, here's the cool thing. When you look at a forest, what you're looking at is solid, ancient air. Isn't that cool? I love that. You're looking at sunlight glued air that has been glued into a shape. Okay, so essentially, photosynthesis pulls carbon out of the air and into living tissue. Now the carbon has to come back. There are 3 ways that it can come back. Respiration, which every living thing, including the plant itself, including you, burns sugar for energy and breathes out CO2. You are, in a very literal sense, exhaling carbon that a plant pulled out of the sky. Carbon goes from life back to air. That is the feedback loop. Hang on, let's look at this again. We as life, plant biomass, if we die, we sink carbon. If we exhale, we expel carbon in the form of plant respiration. Right there. Okay, that's what we're talking about. Now, the other thing is decomposition, right? Things die. Microbes and fungi break the body down, and it releases the carbon back into the air and back into the soil. Rot is just the fast cycle closing that respiration loop, right? So here we go. We have photosynthesis. Air goes into a leaf. Respiration, life makes air. Decomposition, body releases air and soil. The other thing, the other way that carbon has to come back to the atmosphere is through combustion. And I didn't put that on this chart. Combustion, meaning burning a tree, does in an afternoon what rot would take decades, years, sometimes hundreds of years to do, dumping that stored carbon straight back into the atmosphere. Okay, now that's really important. So let me show you something really, really cool. So air, plant, animal, soil, back to air, photosynthesis in, respiration, decomposition out. In a healthy, natural system, those two, photosynthesis, respiration, and decomposition, right? Photosynthesis is one, branching, becoming respiration or decomposition. That system balances. The amount of carbon plants pull down each year is close to the amount that respiration and rot put back up. It literally breathes. I have been part of studies where I have walked into a forest every single day for 2 years, and I have literally sat and measured the breathing profile of a forest. You can physically see on a spectrometer a forest breathing. Okay? It is the coolest thing in the world. The whole biosphere is basically one enormous set of lungs, and it has a seasonal rhythm that you can actually measure. So let's talk about what those measurements look like. So this is a Keeling curve. Yay! Do you see that big line? Now, if I zoom in on each one of those little, hang on. If I zoom in on each of these little sawtooths right here, that's this thing. And I'm going to explain what the Keeling curve does here in just a second. Those little sawtooth wiggles, ignore the overall climb for 1 second. That I will explain in just a minute. Yeah, it is pretty cool that you can measure a plant respiration. But I just want you to look at those teeth. Okay, up, down, up, down, up, down, up, down. The red lines. Those are a single year. CO2 dips every northern hemisphere summer because that's where most of the plants, land, and forest are. And those plants inhale at once when they leaf out. Okay? Then it rises back every winter when they drop their leaves and the leaves rot, right? When they respirate or when they start to decompose. That wiggle that we see, the up, down, up, down, up, down, up, down, the sawtooths, is literally the entire land biosphere breathing out once a year. And we can see it from the mountaintop of Mauna Loa in Hawaii. Okay? That is considered the, quote, fast cycle. And we can see it every single year. The chart that I am showing you right now, known as the Keeling curve, tracks from 1958 to 2024. Data will likely not be available for several years because this data is no longer published by the federal government in the United States, and the NOAA Observatory was defunded. So if we do get additional data, it will be sparser and it may not include all season measurements, which is kind of crazy to think that we've had continuous data since 1958. Now, the ocean is a fast cycle too. And we'll talk about, so we talked about like the mountains, right? But we can also talk about the ocean. Let me go back up here for a second. The ocean is kind of cool because, no pun intended, because I'm going to lean over for a second. On this, on the right side is a really pretty thing that talks about net ocean uptake. But over here on the right, on the left image, you can see the process too. So CO2 dissolves straight into seawater, the same as fizz in a soda water or a soda can, right? Cold water holds more. This is important. Cold water is capable of holding more carbon. Warm water holds less. This is exactly why a warm soda gets flat faster. And the ocean has been quietly absorbing something like 1/4 to 1/3 of all the carbon in the carbon cycle, all of the carbon we put out. Which sounds like the ocean is doing us an enormous favor, because it is. And it's going to send us the bill later. So I want you to hold on to that thread, okay? So the reason that the ocean is important and why this respiration cycle is important is because we are capable of reading the air and we can tell exactly where carbon came from. Why can we tell that? Well, there's something called isotopes. Scientists are able to tell exactly where a carbon atom is coming from. Not a guess, we can actually read it. There are ratios that we can read. So we have light, medium, and heavy, or light, heavy, and radioactive. Okay, so a light carbon is carbon 12. Okay, carbon will always have 6 protons. That's what makes it carbon on the periodic table. But the number of neutrons can vary, and those variants are what we refer to as isotopes. 3 of those isotopes matter to us. Carbon 12 is a stable carbon molecule, the lightweight one. It has 6 protons matched with 6 neutrons. It's the most common. It makes up about 99% of all carbon. Okay? Carbon 13 is 6 protons and 7 neutrons. It's stable, but it's rarer. It's about 1%. It's not quite 1%. I think it's like 0.8. And it's slightly heavier. Now, carbon 14 has 6 protons, but 8 neutrons. It's considered radioactive. It's unstable, and it slowly falls apart at a known clockwork rate. It's heavy, and it's a ticking clock, and that is why we can do something called carbon dating. It is an age clock. We can look at the half-life of those carbon molecules and where they are in their decay cycle, and we can tell exactly how old those carbon molecules are. So 2 of these are detective tools, right? If that is the case, then 2 of these are detective tools. C13 is what I like to consider the source. It tells us,
Cattle?
this is just really freaking cool to me. So when a plant does photosynthesis, it finds it very mildly slightly easier to grab lighter C12 molecules than the heavier C13 molecule. Okay, it's also the more abundant. So it makes sense that plants would have evolved to preferentially absorb C12 rather than C13. It's a featherweight difference, but it's real, and it is consistent throughout the geologic record. That's important. The geologic record, okay? So all living tissue ends up a little richer in C12 than the air it pulled from. In essence, life leans light. So let's follow that logic. Fossil fuels are ancient plants, coal, oil, gas, all of it starts as a living thing that photosynthesized. So fossil fuels carry the same signature. They are, quote, depleted with respect to carbon 13, aka fossil fuels lean light because life leans light. Okay? So when you burn fossil fuel, you dump a flood of that light carbon 13 poor carbon into the atmosphere. So if the extra CO2 in the atmosphere is coming from a fossil fuel, then the air itself should be getting, quote, lighter over time, meaning there should be more C12 than C13 in the atmosphere over time. The ratio, essentially, between C13 and C12 should drop. Yes, Foxter, you have a question over on YouTube. What's up? I'm going to wait for the question. How does the neutron get added? Because neutrons are not positive or negative, the molecules can basically attract a certain number of neutrons to attach. Um, the exact process has electrostatic associated with it. Like some electrostatic charges. Hang on, let me see if I can pull up something for you really quick. Yeah, let me see if there's a simple way um is basically like, have you ever heard of a particle accelerator? This is the easiest way to explain it. You got to see in chemistry, totally fine. Okay. So, let's say so the outer part of a molecule, let me do it like this. Okay. The outer part of a molecule is where electrons the rings on the outside are where electrons get stored. Those are the open slots where other molecules can attach to each other. The inside ring, also known as the nucleus of an atom, is neutral, and neutrons obviously reside in the middle. The atoms can hold, depending on the kind of atom, they can hold a certain number of protons, and that describes the periodic table of elements. Neutrons, however, often get added in an atomic nucleus rather than a chemical molecule, meaning on the inside of the atom and not on the outer ring of an atom, through processes like nuclear reaction. So that's why we can have nuclear reactors. We can force neutrons and force radioactive decay. We can do neutron capture. You can have cosmic ray collisions, or you can do particle bombardment. But atmospheric, yes, heat disrupts the stability. Atmospheric collisions are where cosmic rays from space strike the upper atmosphere and create, quote, free neutrons. And those free neutrons need to find a home, and they will preferentially attach to certain atoms in the atmosphere. And because the atmosphere has a limited number of molecules in it, it will preferentially seek out lighter atoms, lighter elements to attach to. You can also do like proton-neutron swaps, which is where a neutron hits a common like nitrogen-14 atom in the air. It knocks a proton out of that atom, so now you get a free nitrogen proton, but it transforms that atom from nitrogen-14 to carbon-14, and that's how you get these two extra atoms. And so that's primarily the process that creates like radioactive atoms. Great question. Okay. That's what like proton accelerators and stuff like that is. Okay. So we talked about the healing curve. We talked about where carbon comes from. So what ends up happening, right? We talked about plants will preferentially choose C12. That means that the atmosphere is richer in C13 than C12, not like en masse, because remember, C12 is the most abundant form of that isotope. But what we're able to do is when those fossil fuels are burned, we can see that extra CO2 in the air, and the ratio C13 to C12 that is dropping, and we can go, oh my God, that's what's happening. So as CO2 has climbed, the air has gotten isotopically lighter, sliding right toward the, quote, fossil fuel signature. And this is the same, this has a name, sorry, it's called the Seuss effect. It has a chemical fingerprint, and it points straight back to burning ancient plants. So it rolls out. There's a lot of people that will say it's just volcanoes or it's just the ocean venting, because those carbon sources have a totally different isotopic signature than ancient plant residue being burned. And it's a big part of how we know, not assume, we know that extra carbon is coming from human activity. So I want to know, does this help you understand when you hear carbon budget or changes in carbon emissions? Does this help you understand like what scientists are talking about? You can drop emotes. The second part is C14 because that tells you the age of something. So C14 is more like a clock rather than a fingerprint. Because it's radioactive, it decays at a fixed rate after a thing dies and it stops taking in fresh oxygen. So if you measure how much C14 is left, you can date how long ago something died. So radiocarbon dating is when we date wood, bone, charcoal, the works, and we get a total amount of daughter C14 that remains in the rock or remains in that record, and we're able to tell how much time has passed since that thing was last breathing, was last respirating carbon. Okay, so here is the elegant part that starts to tie all of this together. This is the carbon fingerprint, exactly, or the carbon footprint. Well, kind of. I'll explain carbon footprint too. So fossil fuels are so old, they're hundreds of millions of years old, that all of their carbon-14 has long since decayed away. In many cases, it's completely gone. So fossil fuel is considered, quote, dead carbon. There's no radiocarbon left at all, which means burning it.
What? I can't hear you.
What's the tech issue, Diana? Hey, Diana. When you burn it, it dumps C14 free CO2 into the atmosphere, and it dilutes the atmosphere radiocarbon 2. My slump passing out in the car. No worries, Diana. Get home safely. I'm glad that you're making it home from your con this week. So there's two different isotopes, right? Same verdict from two totally different independent kinds of measurement. We can look at the C13 to C12 ratio in the atmosphere overall, and we know that it is depleted relative to the C13. And we know that the burning of fossil fuel is releasing C12 into the atmosphere at a faster rate. And then we can also look at C14 depleted sources and see that the atoms, the molecules that are in the atmosphere, are C14 free. And we also know that this is not being released from a rock cycle like volcanics or plants being like modern plants being burned, because modern plants won't have will have higher concentrations of C14. They won't be depleted yet because those haven't decayed away. And so we're able to say definitively these are C14 or C14 free and C13 depleted carbon molecules, meaning atmospheric concentrations are increasing due to sources, anthropogenic sources, the burning of these fossil sources. So crude doesn't register any C14. Yes, and gets a little more complicated. Depends on the kind of fossil sources that are being burned. And that is why many people try to are advocating for source fingerprinting of CO2, atmospheric CO2. That gets into more of like policy and technology and like carbon management systems. But generally speaking, fossil fuels that have been dormant long enough will not have C14 associated with them. So en masse, they are C14 depleted. So the other cool thing is oxygen isotopes do the same thing. Oxygen tells us temperature, though. So quick one to round it out. There's a light version and a heavy version of oxygen 16 and oxygen 18. And it turns out water made of a lighter oxygen evaporates a little more easily. So the ratio of heavy to light oxygen locked into ice and into shells of ancient sea creatures depend on how warm it was when they were formed. If you pull that ratio out of an ice core or sea floor shells, and you end up with a thermometer for a time before any thermometers existed. So carbon isotopes tell us the source and the age. Oxygen isotopes tell us the ancient temperature, and together we use the two of those ratios to reconstruct ancient climates. So the whole history of the Earth is written in which isotopes ended up where. How is the normal outfit somehow more lewd? I don't know how it's more lewd. It shouldn't be. Okay. Please don't send me to the office for being tardy. No worries, no worries. Bahamut, how are you doing? Okay, so let's talk about this. Let's talk about the deep time and the slow cycle. So the slow cycle. Peat turns into lignite. Lignite turns into coal. This is the geologic cycle. This is where I get to be a rock nerd on Maine, right? Most carbon that dies gets recycled fast, and we just did that. We just talked about it. Rot, respiration, put it back in the air within years. But every so often, a tiny fraction doesn't get recycled all the way. I have to potty. I know you said to go before class, but I didn't want to have to go before class. Bahamut, please go use the potty. If you sprinkle when you tinkle, be a sweetie, wipe the seedy, and make sure that you wash your hands before you come back to class, okay? So a plant falls into a swamp. That's what this little diagram is over here, right? A plant dies, it falls into stagnant water, and it gets buried before it can fully rot. It sinks to the bottom of that stagnant water, which is anoxic. It is oxygen depleted, and that makes it so that microbes can't munch on those dead leaves, and so it can't release the CO2. Sea creatures die, and their shells rain down to the seafloor. There is a constant slow rain of dead bodies through the oceanic water column into the deep sea, and that carbon gets buried, and then it gets buried deeper. And then heat and pressure and time go to work. So two big things can happen down there, okay? And they're two long-term storage things. Buried plants become a fossil fuel. Peat becomes lignite when it's like poorly compressed. And then if it gets buried hotter for longer, it becomes bituminous coal, or some people will say bitumen. And then anthracite is when carbon is totally locked, and it is the hardest, most carbon dense hydrocarbon that exists. After anthracite, you go to graphite and ultimately to a diamond. Okay? This process becomes oil and gas, or it can become so locked that it becomes inertite, which means the carbon is no longer mobile. Buried shells in the sea become limestone. So those sea creatures that built their shells out of calcium carbonate, they pile up, they compress, they get turned into a rock. And the largest pool of carbon on the Earth is actually not the atmosphere, it's not the forests, it's not the ocean. It's carbonate rock, limestone. It's the fossilized bodies of ancient sea life. The White Cliffs of Dover are made of it. We've talked about that before. The Travertine Terraces,
Petals?
made of it. That's what the carbon reservoir, that's an example of a carbon reservoir that you can stand on. But here's the important thing. Once carbon is in that rock, it's out of the game. It can sit locked away for hundreds or millions of years. The only way it naturally comes back into the carbon, quote, stock for the Earth is if volcanoes burp it out, rain slowly weathers the rock because rain is slightly acidic. It rains on limestone. It will eventually release that carbon. And it slowly shuffles the carbon around over a geologic time scale. It's a trickle. It's like a stalactite building in a cave. This slow cycle is called slow for a reason because the carbon is moving on a clock that's where thousands of years is considered a rounding error, okay? Hundreds of millions of years. And these rock are also fossil fuel. This is an important thing to remember. So I want to give you a reframe that I think is really, really, really cool. Carbon is stored, coal is stored sunlight. It's a solar battery. The energy in a lump of coal is sunlight that hit a fern 300 million years ago, got packed into that plant. It got buried before anything could spend it, and it's been sitting in the dark ever since. So when you burn coal, you're spending sunlight from before the dinosaurs walked the earth, right? So you're releasing an afternoon of carboniferous sunshine that got put into a savings account and then forgotten about. So here's the question to sit with for you, right? If that carbon was going to come back out eventually through volcanoes and weathering, why does it matter if we're letting it out now in the form of fossil fuel combustion? Does it matter at all? Take you back to this graphic. Heat to lignite, bituminous coal, anthracite. Okay, ultimately, it's not that the carbon is coming back, it's that the rate of it is astronomically high. Nature would have released that buried carbon over millions of years, slow enough for the whole system to mass balance it. Ocean, life, climate, it gets to adjust around that in real time. But if that is being released over a couple of centuries, the same amount of carbon that was stored in those plants for hundreds of millions of years is being released over a couple of centuries, it's not about the destination, it's actually about the speed at which it's getting released. Because we have a desired climate range, ideally, there's a non-zero chance that some of the light that was released from the particles eventually formed the Earth and in time is hitting us each night. When you see starlight, you are possibly seeing your own past in a cosmic sense. This is true. So, let's talk about the PETM. There is a geologic marker that exists at 56 million years ago, and there is a temperature spike associated with that 56 million year ago. So there's a oxygen isotope measurement that exists around the world at exactly when the Paleocene and the Eocene boundary exists. It's known as the Paleocene Eocene thermal maximum, or the PETM. It's a massive slug of carbon that got released into the atmosphere and ocean, most likely in the form of a volcanic eruption. That is the most likely theory. But the planet responded exactly the way physics said it should. global temperatures jumped roughly 5 to 8 degrees Celsius, the oceans acidified, whole populations of deep sea organisms went extinct, and you can see it as a distinct layer in seafloor sediment core. It's a band where shelled creatures dissolve and chemistry lurches over a cliff. It's written into the rock as clearly as a bookmark. Am I going to release this as an edited VOD on YouTube? All of these end up going, like, they're live on YouTube now, and they'll just roll over. I'm working on a whole series where we're going to release these as videos, like as edited videos. So here's the cool thing. The scientists studied PETM precisely because it's the closest natural analog we have to what's happening now. And here's the sobering part about it, and the part that lands with the 2 clock idea, right? When researchers work out the numbers, our current carbon release is happening 9 to 10 times faster than the PETM. And that was the most dramatic carbon release event in 66 million years, but we're outrunning it by a lot, So when someone says the climate has always changed, they are right. That is absolutely right. The PETM is one of the best examples of it, but the honest version of that sentence finishes, the climate has changed before, and the times it's changed this fast, it went badly for a lot of what was alive. The rocks, in essence, keep that receipt of that too. So, the reason is it's not brute force. Isn't our current carbon release rate the reason why we're having scorching hot summers? Well, it's why climatic patterns are being disrupted. And it's because we have an unmatched faucet and we have no drain. Okay? So let me tell you, like, the whole idea behind this is we put slow carbon on a fast clock, or we threw the cycle out of balance. Okay, they're slogans, right? It's something that I call like tweetable science. It's a mnemonic to help you remember what is happening. However, you came for the actual machinery, and we talk about the actual facts behind what is going on. So let me show you exactly how a balanced cycle stops balancing, because the mechanism is not what most people think it is. Okay? Here is what is known as the bathtub model. Emissions are the faucet. That is what we are pouring into the bathtub. And the sinks are considered a drain. They're the things that pull that CO2 out of the atmosphere. Okay? So if water pours from a faucet, water goes down through the drain. That's kind of simply the whole thing. Okay, I'll wait for you guys to come back from ads. I'm going to stand up. Daddy Bezos is hungry. Indeed. At least he's not thirsty. That would be weird. Hang on, guys. I'm still standing up. I'll wait. Ouch! Smart guy, why am I getting bonked? I didn't do it. Daddy Bezos did. Stretch time. Indeed. I'm gonna need more coffee after this, guys. My model does not like me drinking, like, from bottles. She only likes it when I use a straw. It really sucks. It really, really sucks. Okay, I'm hanging on. She's like, she looks like she's getting hit by an invisible wall. See? Or she looks drunk. I'm gonna wait. Look, I see more people coming back. So I'm assuming that you're coming back now? Are you back? Nano, are you okay? Thank you. Thank you for the nose boop. Thank you, thank you, thank you. Okay. How's everybody doing? Are you hanging in there? I'm hungry. Made some old ice cream. Okay, cool. Lots of cleaning today, but happy to learn about the carbon and the big C, one may say. Indeed. Okay, so picture a bathtub, right? Water pours in from the faucet, water goes out through the drain. Here's the only rule that matters. The water level in the tub doesn't depend on how fast the faucet runs. It depends on whether the faucet is running faster than the drain can empty. That's basic physics, right? A faucet faster than drain, level rises. Drain keeps up with faucet, level holds steady. Drain moves faster than faucet, tub empties. That's it. That's the whole thing. Okay? So the CO2 in the atmosphere is the water level in the tub. Here's where most people's intuition goes wrong. So I'm going to slow this all the way down. The natural carbon cycle is a huge faucet and a huge drain, and it's almost perfectly matched. The natural carbon cycle moves staggering amounts of carbon in a single year. Plants pull 120 units of carbon out of the air annually through photosynthesis. Respiration and decay put almost exactly that same 120 back. The ocean breathes something like 90 units in and expresses 90 units back out. Enormous flows, right? Way, 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 way bigger than humans emit. So here's the question that trips everybody up. If nature moves way more carbon than we do, like 10 times more, how could our tiny contributions possibly matter? And here's the answer. It's the key that unlocks everything. Nature's faucet and nature's drain are matched. For thousands of years, 120 going in matched the 120 going out. Huge faucet, huge drain, same size, so the tub level held steady at around 280 ppm, parts per million. The size of the flow was never the point. The balance was the point. So what happened was we walked in and we turned on a second faucet. It was a small one. But here's the thing. Our little faucet has no matching drain. Every year, we add our stream on top of the balanced flow. Nothing in the natural system is set up to take it back out at the same rate we add it in. So what happens over time is the natural water level, quote unquote, in the bathtub creeps upward because it's unmatched, okay? We didn't make nature's faucet bigger. We added a trickle with no drain, and that trickle with no drain running for 200 years fills up the tub. So that's the mechanism. When you hear somebody say, how did we break climate? That's how we broke it. It wasn't brute force. It was an unbalanced addition to a system whose whole stability depended on being balanced on a slow clock and a fast clock scale. So our faucet comes from 3 taps. Let's talk about them. Okay? The first one, the biggest one, is burning fossil fuels, and it's a giant. When we dig up coal, oil, gas, and we burn them, we're taking carbon out of the slow cycle and putting it out, pulling it out of its deep geologic storage locker and injecting it into the fast cycle. And then we're saying it's okay, trees and the ocean can absorb it. Spoiler alert, it can't. Okay? The brand new carbon is, as far as the fast cycle is concerned, it was carbon that was safely out of the game for another 100,000 years, 100 million years, okay? So critically, it's one direction. It goes in, but there's no way to sink it out. We only ever pull it up and burn it, right? There's no natural process for putting it back on any timescale that matters to us. And this is the tap that's being run wide open since the Industrial Revolution. It was literally a switch we turned on when we moved from whale oil to coal. And it's the overwhelming majority of the problem. The second problem is cutting down trees or, quote, land use changes, okay? This one's a little sneaky because it's a double hit. When you burn and clear a forest, first, you release all of that carbon that was stored in those trees, and that's considered a one-time dump into the atmosphere. But second, and this is the part that people miss, we just destroyed part of the drain. That forest was a working sink. It was pulling carbon down every single year. So deforestation turns a piece of the atmospheric drain at the exact moment it dumps more into the atmosphere. It turns it off. So it fills faster, it empties slower, and it's both from a single act. Tap 3 is the quiet one, weakening sinks. So here's the cruel twist of fate. Remember that the ocean and the forest have been absorbing about half of everything that we emit. Half. They've been quietly bailing out our bathtub this whole time. And without them, the level would be far higher than it is today. Okay? But we covered why they're struggling. We covered them a little bit, right? Warm water holds less CO2, so the ocean drain shrinks as it gets warmer. Forests hit by drought and fire have smaller cellular structures, so they can physically absorb less carbon. They can physically respirate less carbon. So the land drain sinks too. So the drains are getting smaller precisely because the tub is getting taller, has more water in it, which means the more our faucet stays on in the tub, the system's own safety valves are closing under the strain of that added water or that added stream into the tub, okay? So putting that together, both of those things together, is the real mechanical answer as to how human activity, quote, broke the carbon cycle. It was never that we outmuscled nature's enormous flows, right? It was that we added an unmatched one-directional faucet, mostly from fossil fuels. We simultaneously smashed part of the drain by clearing land and changing land use, old-growth forests. And now the remaining drains are weakening under the heat that we've already caused. So faucet up, drain down from 3 directions all at once. The tub fills, the water level, the thing that we actually measure. And this is where it's staggering, guys. We went from a stable 280 ppm, parts per million, of carbon in our atmosphere that had been stable for millennia to 430 parts per million in the blink of a geological eye. It was quite literally in 200 years. And notice, because this matters for later, the bathtub also tells you the fix. Because you don't have to bail the whole tub. All you have to do is turn the faucet down until that drain can catch up. That's it. That's what every climate target on Earth is actually describing. When you hear scientists talk about holding global temperature at 1.5 degrees C or 2 degrees C, or reducing atmospheric emissions, that is scientists saying there are technologies and tools at our disposal to get our unmatched faucet back down to where the drain can naturally balance on the fast clock cycle, so that the slow clock cycle can start to regenerate the carbon that we have used. The bathtub is the problem, but it's also the instructional manual as well. And so this is where CO2 becomes a quote greenhouse gas. Okay, so let's nail it down because greenhouse gas gets said a lot and it's never really explained. And it's super not complicated. Sunlight comes in as mostly visible light, right? It's shortwave, and most of it passes right through the atmosphere and it hits the ground. When the ground heats up, it radiates that energy back towards space. But now it's infrared, it's long wave, it's heat radiation. So here's the trick. CO2 is transparent to the incoming, predominantly short wave visible light, but it absorbs outgoing infrared light. So energy gets in really, really easy, and then it has a really hard time making it out of the atmosphere. The heat gets caught on the way out, and it gets re-radiated in all directions, including back down. Now, this is where people either over panic or they dismiss it, and both of these groups are wrong. Okay? The greenhouse effect is not a villain. It's the reason the Earth isn't a frozen rock. Without any greenhouse gases at all, the planet's average temperature would be well below freezing and none of us would be here. We need that atmospheric blanket. The problem isn't the blanket. The problem is that we made the blanket thicker, fast, by moving all of the slow cycle carbon into the fast cycle. So that means more CO2, more outgoing heat getting caught, more energy staying in the system. And more energy in the climate system is what's underneath all of the symptoms people argue about: melting ice, higher seas, stronger storms carrying more water, shifting USDA growing zones, longer summers, more dramatic heat waves, drought, etc., etc. It's not that every warm day is climate change. That's not it. That's not it. It's that you've loaded more energy into the whole climatic system, and the system with more energy behaves more extremely and is more erratic. Okay, so we can prove this is called a theory, right? This is called a theory. This is that number. I have to show this to you again because this is just dramatic. 280 to 430. Higher than anything, and I'm about to show you why. We're able to keep track of parts per million of CO2 using ice core air, so literally air trapped in Antarctic ice. The jump from 280 to 430 is the jump from pre-industrialization to 2025 peak. That took about 150 years. And if we look at it en masse, it is literally 100,000 times the natural pace of CO2 rise. Okay, so hang on. This is the cycle. So this is 800,000 years ago. Okay, 700, 600, all the way over. And this is off the chart, right? This is year zero. This is quote 0 years ago from when this was published. I think the Epica Dome C and Vostok measurements were last done in like 2023. Okay, so this was like, like, no, 2020 maybe, because it was like not 400 yet. But now this chart is 430 ppm, atmospheric CO2, okay? The other thing that we're measuring, remember, because oxygen, temperature anomalies in degrees C, we can convert temperature anomalies and we can show glacial maximums, glacial minimums, max sea ice, minimum sea ice, et cetera, et cetera. Like that's what the Vostok and Epica data sets are used for. Okay, so we can prove CO2 is genuinely historically weird right now because we have the actual air from almost a millennia, almost a geologic epoch ago, okay, in the form of ice cores. So when snow falls in Antarctica and Greenland and it gets buried and compressed into ice, it traps tiny bubbles of the atmosphere from that year, okay? From that year. When you drill down through those layers of ice and you capture them in a sealed tube, you are literally picking up samples of ancient air from hundreds of thousands years ago. You can measure the CO2 in the bubble of sky from before humans existed. And for the last 800 years, CO2 swung up and down roughly between, hang on, let me move this way, roughly between 180 and 280-ish parts per million. We had ice ages, we had warm, like hothouse planets, we had warm periods. But if you see the rhythm, roughly speaking, right? Roughly speaking, there is a cyclicity to it. And it goes up and it comes down and goes up and it comes down. But it stayed within this major kind of stable band. And that is the stable band at which life can operate because the sources and the sinks keep pace with one another. Is the atmosphere thinning or thickening, or is composition changing? Great question, Foxter. When you hear about atmospheric thinning, what they're talking about is the ozone layer. And that was depleted because of CFCs and HCFCs, or hydrocarbon fluorocarbons, or carbon fluorocarbons, which predominantly, as the ozone got really, really thin in the 80s and early 90s, was quite literally because of refrigerants and hairsprays. That can be fixed on a human timescale. Carbon timescale is a geologic timescale issue. So it's the composition of the atmosphere that's shifting over time, becoming denser with CO2 relative to hydrogen, nitrogen, helium, all of the other little bits that make up our planetary atmosphere. So as of 2025, we crossed 430 ppm at the seasonal peak. So that's more than 50% above pre-industrial averages. It's higher than anything in the entire 800,000 year ice record that exists on the Earth. And it happened in 150 years, right? The modern line doesn't actually curve up. If you can see it, it goes straight vertical. It is literally the wall of the North from Game of Thrones. Like, it is a wall. It is a literal wall. And the important thing about it is that wall coincides with the Industrial Revolution, with the proliferation of coal-fired power plants and coal-fired activity, like smelting, making clinker, like all of these CO2 intensive industries that added over time. Okay, but I do want to be fair and I do want to be complete, because there is a cyclicity that exists, and it is fair to say if there is a cycle that went up, we're in an up and it should go back down, okay? And there are natural swings, they are real, they have real causes, and knowing them is how you can tell normal change apart from other change, okay? So there's 3 big natural drivers, and they run on the slow clock. Remember this, they run on the slow clock. So we have orbital wobbles. They're also known as the Milankovitch cycle, okay? Earth's orbit is not actually fixed. The shape of it stretches and it rounds out over time. And then we have a tilt of the axis of the Earth that nods up and down. So the whole planet wobbles like a slowing top, all on cycles of roughly 10,000 years. Okay, so those shifts change how much sunlight hits, where it hits, and when it hits. That is called, I'm going to call that the metronome behind the ice ages. Okay, so this is the rhythm that makes the sawtooths in this graph. Like when it goes up and down and up and down and up and down. If this is 100,000 years, there's roughly 10 Milankovitch cycles in that 100-year period. And if we zoom in on this graph, you will see 10 up and downs associated with temperature anomalies, okay? The second one happens over millions of years, but volcanoes are the slow cycles release valve, trickling CO2 as it melts carbonate-rich rock into magma and then expresses CO2 gas. It releases that CO2 back out of the rock. And a single big eruption can throw up a haze of particles that cools the planet for a year or two because it shades it from incoming shortwave sunlight. Okay? It's real, but it's small compared to what, like, the levels of change that we see, and it barely shows up in something like the ice record. It is more likely to show up as an ash layer or the depleted C14 in a in an ash layer, etc., etc. Okay. And then the final one is plate tectonics. So on the longest scale, continents move, mountain ranges rise, and they weather away. Ocean currents get rerouted around continents, but that happens on tens of millions of years, and that forces a reshape of the whole climate. That's why at equatorial regions, we see a lot of limestone forming, or a lot of coral reefs, right? But at the extreme ends of plates, we see a lot of volcanism, like the Ring of Fire in the Pacific or the Caribbean, like we talked about last week. And like, the whole point of this is all of these are happening. Every single one of them is slow. Very, very, very freaking slow. Like, crazy slow. Tens of thousands to millions of years. And that is what scientists and life on Earth consider to be the natural tempo of climate change. What we've done is drive a change of similar size in about a century and a half by yanking carbon off of the small clock. So when somebody says climate has always changed, that answer is accurate. It's a yes and, though. Yes and, here are the 3 ways it does it, and all 3 take basically forever compared to us. Same destination the planet has visited before, we're just taking a rocket ship to get there, okay? So the ocean sends us the bill. The ocean absorbs on an annual basis about 1/4 of our total carbon emissions, but it's paying for it. So why is it paying for it? More CO2 in the atmosphere creates more carbonic acid. More carbonic acid means more hydrogen ions. They grab carbonate, and that means shells starve. Okay, this is the natural process that occurs. Carbonate is the exact building block of all coral, and it is what shellfish need in order to form their shells. Acid pulls it out of the water. Let me explain this in some detail, okay? The ocean is something that I consider our hero, and I know that a lot of people have thalassophobia. I understand that. I really think that you should have a healthy appreciation for how incredibly gorgeous our oceans are, and because of what it does for you. CO2 dissolves in seawater, but it doesn't just sit there, okay? It reacts with water and it forms carbonic acid. It's the same weak acid that makes soda slightly tangy when you drink it. Okay, so that carbonic acid then breaks apart and it releases hydrogen ions. Hydrogen ions are, by definition, what acidic means. Okay, so if you're talking to somebody in chemistry, those hydrogen atoms are part of the acid of a pH. Okay, so more hydrogen ions lowers the pH, means more acidic water. That's called ocean acidification. Okay, the surface ocean is already about 30% more acidic than before the Industrial Revolution. So we're running like a planetary scale chemistry experiment on the ocean, and we can read the pH meter. Okay, but here's the cruel part, and it's cruel because of how it works, not just because of how it happens. Those extra hydrogen ions don't just float around. They go look for something to bond with because they're not stable. Okay, they're a really clingy X, and they're gonna go grab carbonate ions out of the seawater. Carbonate, Ca3CO2, hold on to this and are the exact building blocks that coral, clams, oysters, sea snails, plankton, huge amount of plankton used to build both their shells and their skeletons. They pull calcium and carbonate out of the water to make calcium carbonate, and that same stuff as the limestone from the slow cycle. I want you to remember this, right? So let's follow the trap. More CO2 in the water, more acid. That means more hydrogen ions. Those ions snatch up carbonate, and now there's less carbonate left in the ocean for the shell builders. We are chemically pulling the raw materials for shells out of the water right as we ask marine life to keep building them to sink more carbon in the atmosphere. In the worst spots, especially cold water, which holds more CO2, the water gets so undersaturated that existing shells start to dissolve. The animals trying to build a house out of a material that's disappearing from the shelves in a pool that's slowly digesting the house that was already built. That's why you see mass migration of shellfish away from historically colder regions right now. They are literally trying to find a place that won't eat them alive. The ocean is trying really, really, really hard to buffer us, but it's paying for it at the same time. It's the sink and the casualty. That's the tension that sits underneath this entire subject. A lot of things absorbing our carbon are the same things that are getting damaged because it's trying to absorb too much. Forests that burn, oceans that acidify. The buffers aren't free, and they certainly aren't bottomless, okay? So what does this mean for us? Okay, so this is a picture. The first image was taken in December of 2024. This is in American Samoa. This is a very, very famous from NOAA, a very famous image from NOAA. The second image on the right is from a survey that was done 3 months later in February of 2015. 3 months later. 3 months later. 3 months after this photo was taken, the entire coral reef was dead. Within 6 months of an ocean acidification event that took less than a year, an entire coral reef in American Samoa was dead. And this is happening all over the world. So what I wanted to do was show you guys, let me pull this up really quick. I'm going to show you a video from a survey that just came out this month, because it's really, really helpful to see it live. Let me go grab it and we'll pull it up here. How am I going to do this? Give me a second, guys. Because when I usually do this, I usually do it using a video, like an embed. Let me see if it'll actually work here. No, it's not going to work here. I can do it from swap, presenter, and slideshow. I can do it from here. I will show you from let me open this on YouTube. There we go. Yeah, I'll just open it on YouTube really quick for you.
Scientists have seen the first.
And this is Teacher Rocks. Let me see. Is this video distorted? Yes, it is. Okay, here you go. So this is that video. So this was this year. Okay, this was this year. This was literally 3 weeks ago. Noah just published it. This is in the Florida Keys.
During routine coral monitoring on July 7th.
This was on July 7th. The Atlantic Oceanographic and Meteorological Lab looked at Chica Rocks. It's a shallow spot off in the Florida Keys, near Isla Morada. And this is a top scuba diving destination because it is so incredibly luscious. They expel symbiotic algae when they start dying. This was in 2023. It had a bleaching event in 2023, right? There's the bleaching threshold on the water temperature and surface temperature. In 2026, it started way earlier. We're not even into September, right? The peak event that caused bleaching and killed off so much of it happened in September, October of that year. This is July, and we've already outpaced it, which I find insane. Whoops. Now, there are so incredible incredible people that work on ocean restoration and coral restoration projects. There are actually programs where you can buy spots, like pay scientists to start growing new coral to rehabilitate coral reefs by reseeding the coral. And I contribute to a lot of those projects for this very reason. It is absolutely gorgeous. And a great thing to do for like holiday presents and stuff for folks. But okay, so let's kind of continue on here, right? So one more layer, because it's the part of climate science that keeps scientists up at night. How do you grow coral? You basically create nurseries where these little shellfish that form the coral colonies over time. You create basically an incubator in the open ocean, and you train the coral to be able to adapt to the changes in that ocean, in that environment over time. And then you take it back out and you repopulate the reef with these little seeds, and then they take over and they basically build new colonies for their little microorganism communities on top of the skeleton of the now dead reef. Correct. So, okay, so a feedback loop is when a change causes more of itself. And when a carbon system has kind of some nasty ones where warming causes more carbon to release, which causes more warming. And so the three worth noting are permafrost, ice, and the albedo effect. Not libido, albedo, and warm water holds less CO2, which we just saw, right? So as the ocean warms, its ability to hold dissolved carbon drops. So the hotter it gets, the less carbon our oceans can keep taking in, which leaves more of it in the air, making it hotter. And so the best buffer that we have gets weaker exactly when we lean on it the hardest. Permafrost is the frozen ground across the Arctic and Arctic regions, and it has enormous amounts of dead plant matter that it's locked in. It's carbon that's quite literally put on ice for thousands of years. And when we start to warm the Arctic, the permafrost thaws, microbes wake up, start eating that old carbon, and they start burping out CO2 and methane, which warms things more, which thaws more permafrost. And you see that loop. It's the slow cycle carbon that got moved to the fast cycle without us even having to burn it. It's just literally warming the freezer and like defrosting the freezer, right? And then ice and albedo. So bright ice reflects sunlight straight back into space. It doesn't absorb and send back only the radiatives. It sends more of those short waves back too. So when what melts, it uncovers dark ocean or dark ground, which absorbs sunlight instead of reflecting it. So melting ice causes more warming, which melts more ice. And that creates a chain reaction where the planet's mirror gets smaller and smaller and smaller the more you use it up. Okay? So I'm not saying all of this as a doomsday switch that's like already flipped. That's not an honest read. A lot of people try to sell you that way, and I'm not going to do that because I am a scientist. What I am saying is that the system has these loops built into it, and they're the reason that the rate of emissions matters so much. A slow nudge, the system can absorb. A fast shove, and you risk waking up these loops that keep going on their own. Once they're triggered, it's really hard to slow them down, and that's the real argument for moving quickly, okay? Some of these doors are easier to keep shut than others, okay? So we have sources and we have sinks, right? We've talked about this. A carbon source or a carbon sink absorbs more carbon than it releases. Forest, healthy soil, peat bogs, the ocean, over the long haul, even carbonate rock. A carbon source releases more than it absorbs. Volcanoes, burning fossil fuels, deforestation, melting ice. And the sharp point, the point that makes this kind of a live thing and not a chart, the same object can be either, depending on what you do to it. A standing forest is a sink, pulling carbon down every summer, but you burn it, you clear it, and it flips to a source in an afternoon, dumping decades of stored carbon all at once. And the Amazon has been tipping toward that line in places from a sink toward a source because of deforestation for rangeland cattle grazing, as well as fire caused by extreme heat events. We're also seeing that in Canada right now. The label isn't fixed to the object. It depends on how it's treated, which means that it's a lever. Okay, so old growth forest is a sink. Let's talk about a coal power plant. Is that a source or a sink? This is a question. Chat, you get to shout it out. Is a coal-fired power plant a source or a sink? It's a source. Yes, correct. A peat bog. Is it a source or a sink? Peat bog. It's a sink until what happens to it? Till something changes, right? Think as long as it isn't coughing up the stored carbon. Precisely. Yep. Okay. What about a volcano? What a volcano? Is it a source or a sink? It's a source, correct. How about the ocean? A source or a sink? Technically, on this slide, we're calling it a sink, but is it? It's both. Yes, Tronsky. Yes, it is. It's both. What about a thawing permafrost bog? A thawing permafrost bog is a source because it's rotting. Was a sink, now a source. Yes, exactly. What about a living coral reef? A living coral reef. A living coral reef. It's alive. Is it a source of carbon or is it a sink? It would be a sink until it acidifies. So technically it can be both. Right? So here's the cool thing. How do we pull the lever on this? Well, we turn the faucet down until the drain can catch up. So we can put less in, right? This is a big one. Every ton of coal, oil, gas we don't burn is the slow cycle carbon that stays on the slow clock where it belongs. That's the whole ball game, and that's why the energy transition, or what people say, of like moving to solar, wind, nuclear isn't just a side quest. Okay, that is quite literally the carbon cycle intervention. When you swap a coal plant for a wind farm, you're physically choosing not to move ancient carbon into modern air. It's the same with efficiency, right? You're losing less energy for the same job, which means less carbon has to be moved, full stop. Okay, now energy efficiency is not a sexy solution, so it doesn't win a lot of people's attention. However, industrialization has done a lot to improve life expectancy for human beings as well as quality of life around the world. So saying that because industrialized nations have already gone through their revolutions and have predominantly contributed to the overall carbon stock, now industrializing nations or emerging nations, emerging economic nations, cannot do the same thing is really unjust, because they have often extracted those carbon sources from those emerging nations and stolen their wealth in the process. Okay? So energy efficiency is another way to address it. Insulation, better building materials, more dense city centers, reducing heat islands in urban centers by planting trees, reforestation. All of these things improve efficiency. Okay? It's not showy. There is a really sexy idea that a lot of people have been working on recently, which is carbon management, which is the idea that you can trigger more carbon to move from a source to a sink by using technologies that absorb carbon molecules and turn it into a physical carbon substance that can be turned into carbon bricks, carbon-based like carbon concentrated cements, carbon concentrated steel, carbon pellets, like all kinds of stuff, right? Or like you can make methane and gas out of carbon that you remove from the atmosphere. That's called blue hydrogen, essentially. Okay, so it's like you can do all of these things. You can make hydrogen fuel out of the atmosphere. You can also do mangrove restorations and create new carbon things. You can do reforestation. You can do ocean restoration projects. You can breed a bunch of seaweed and you can sink it to the bottom of the ocean. We can literally create a vacuum and suck it out of the sky. That's called carbon capture, direct air capture. These are all things that exist. They're super, super cool technologies. I've worked on every single one of them, and that's called pulling more out. Okay, that's called pulling more out of the atmosphere. There's two flavors of it. There's natural and there's technological. The natural sinks, which already work, and those are free. And this is the part that I love because it's paying attention to what the planet already does, right? You protect and then you regrow forests, the carbon sinks that run on sunlight. You farm in ways that build carbon into the soil rather than stripping it out. Healthy soil is one of the biggest carbon reservoirs our planet has available. You protect wetlands, you protect peat bogs, mangroves, seagrass. These are really quiet, they're unglamorous ecosystems that lock carbon away fast and they hold on to it on a geologic timescale. None of that is exotic. Okay? It's keeping the sinks we have and it's helping them do the job. But those other things, carbon capture and storage or CCS, direct air capture, that's technological, and that's like putting scrubbers at the top of smokestacks of power plants and factories so that before it hits the air, you pump it deep underground into the rock and you artificially create a slow clock storage system. Basically try to intercept the carbon on its way out and put it back on that slow stock, right? Direct air capture is a machine, like that vacuum, that it's a sci-fi one. There are working examples, but they are not on an industrial scale yet. They are promising technologies. They are genuinely part of the picture, especially for industries that are really hard to, quote, decarbonize, okay? But right now, they're really, really expensive. They're no longer funded with research money. They run at a small scale compared to the size of the problem. And it takes a lot of energy to do these things. Like, requiring either more clean energy, quote unquote, clean relative to carbon is what people mean when they say clean energy. So carbon neutral energies to put it on the grid. Clean does not mean conflict free, and it does not mean planet conscious. Okay. Solar requires a lot of mining. So do wind farms.
I
They
just
use
needed
up
you to
land
know.
use, all kinds of
I
stuff.
love you.
I love you too. Love you too, Twisty. But they are clean relative to carbon, okay? But the honest framing is capture tech is a real tool. It's not a permission slip. And this is what my job was up until January. It doesn't let us skip move one. Anybody selling it as we can keep burning everything we want, machines will fix it later, is skipping the math. It's
Cattle?
not an and, it's an and, it's not an instead. Okay, we have to turn off the tap and remove stock from the tank so that we can rebalance the carbon budget. Okay? Here's the thing that science alone doesn't tell you, and that's why science communicators like me exist. Which lever gets pulled? How hard it gets pulled? How fast? It isn't physics that does that, it's people. There are three things working together: policy, the rules and the targets and the agreements that decide what's allowed and what's paid for. Then you have technology, the innovation that keeps things moving towards cleaner options and making those options cheaper and better, and making sure that they are available in the places that need them most. And then social demand, regular people deciding that this matters and pushing for it. Those three things pull on each other constantly. Public pressure moves policy. Policy funds technology. Cheaper technology makes it possible for the public to choose better options. And that flywheel is how big systems actually turn. Okay? And I bring this up because it's easy to walk away from this entire lecture feeling like the whole thing is happening at a scale that you can't touch. But you just learned to read an entire carbon system, a planetary scale system. You can tell a sink from a source. You can explain isotope fingerprints, and you know why the climate always
Cattle?
changed is true and also incomplete. That literacy is everything, because now you have this social demand lever that's made up of people who understand what they're asking for and why. And being able to do that is what you all are now qualified to do. The technology exists, the tools exist, all of these things do exist. But because we don't teach the carbon cycle at this level of complexity, no matter where you are in your education system, whether you went to college, you're in college, you're still in high school, you never went to college, whatever it is, this is legible to you, right? Like, we all understand a bathtub. So it's actually a disservice for us to not teach the public these things because we're afraid of what it means on a political or social basis. And we don't want to be labeled as woke, or we don't want to be labeled as like a drill baby drill or whatever it is. These are not, it's not, that should not be part of the equation. Okay. Because there are objective truths and objective observations that we can make that help inform us and help us each individually make better decisions. And when we each make better decisions and say, hey, I understand, and I know that you may not, and if you're willing to have a very hard conversation with me, maybe we can both come to more of an understanding together. That is how things change. Energy transitions have happened since energy became a fuel source for humanity. We started with biomass, we went to whale oil, we went to coal, we went to kerosene, then we went to oil, and now we're moving towards hydrogen and other fuel sources. Things will continue to evolve. It doesn't mean people aren't needed. It doesn't mean those jobs don't exist. It doesn't make people that worked in previous forms of energy evil. Doesn't make them evil. When we know better, we can do better. And with all of this science underpinning that work, we can do better really, really fast because we can understand working at a system scale and how things are going to move because it's predictable, because it is a mass balance system. So that was our Science Sunday. That was a full-on lecture. That was a full-on 2-hour lecture like I do for colleges around the country. I hope that you guys enjoyed it. Thank you so much for being a part of it. Okay, I'm going to move us to just chatting for a second so I can close this presentation. How are you, Jespo? I'm doing really good. How are you doing? Thank you. Thank you, thank you, thank you. I'm good, thank you. Good. Glad to hear it. Thank you for the hug. Okay, so YouTube, I am going to end this stream and start a new one for our game. So hang out if you're hanging out on the YouTube side. Kick and Twitch, I just need to change categories and rename some stuff. So give me a hot minute to do that. Would you guys like words while we hang out? I'm also happy to answer any questions. Thank you for the lessons on life, the universe, and everything. I think knowledge gives me comfort. I think that's good. Knowledge should give you comfort. Like truly knowledge should be empowering, not terrifying. Honest to God. Okay, YouTube, I'm going to stop here. Thank you guys so much for being here.